I will help you better understand how the torsional vibration, the different types of excitation that are now getting bolted on these low-flying electrical aircraft. So here's roughly the some bullet items I want to cover from a noise and vibration standpoint. These challenges are sort of, I feel like, the top two. One, these aircraft have to get certified, either by the FAA or by ESA. But they also have to pass the public acceptance test, which may even be a bigger hurdle than the certification. So let's talk a little bit about certification from a FAA standpoint. First, some of these things are well defined from a certification standpoint. One of those areas is flutter. So there's two different types of flutter. There's classical flutter, which is basically an instability due to the interaction between aerodynamics, inertial, and elastic forces. But then whirl flutter. And whirl flutter is sort of a new beast in a way that used to be an old problem, and we got away from because we went to the jet engine, the turbine, instead of a propeller. Well, these eVTOL aircraft have adopted the propeller because that is the most efficient way to get the aircraft off the ground at low RPM. Well, now that you have reintroduced the propeller, now you have to deal with whirl flutter, where whirl flutter is basically the stiffness of the housing of where the motor is bolted onto the wing or the different parts of the aircraft, and the excitation of that RPM of the propeller. So that's a little bit about flutter. So we took the HBK's BK Connect, and we took some time data, as you see on the left-hand side here, and processed it. Took a little bit closer look at it in the time domain, but then post-processed it into the frequency domain, which is what you see on the right-hand side here, and did some modal analysis on a small drone. So if you take a closer look at the, I'll call it the electrical data, the torque, the current, the voltage, the speed. If you zoom in and take a closer look, you can see that the torque has got not only a static value to it, but it's got a dynamic riding on top of that static, which, if you think of it, that motor is sitting there oscillating back and forth. Well, if you take a closer look in the frequency domain, that shows up in this example of this data that we took at roughly a little over 8 hertz. It's like, all right, who cares? You're probably not going to hear it. You probably are not going to necessarily feel it. But just so happens that if you look at it from a modal analysis standpoint or a ground vibration test, GVT, that drone had the first wing bending was at 8.9 hertz. Then the lateral fuselage bending was at 9.2, and the vertical fuselage bending was at 17.4. So taking the tools that HBK has, not only from a software hardware standpoint, but also from a transducer standpoint, we did a modal analysis on this drone to see where these bending modes were. And with flutter, basically, if you set right on top of one of these modes, the wings could basically fatigue and fall off. And my colleague Kurt will talk a little bit more about that after I'm done here. But that's why it is such a critical issue And the FAA regulates this, that each aircraft has to be tested part of, I think it's CFR 14, Part 25 certification. So they have to go through this type of analysis where we have progressed to the point where most aircraft either had, 2 jet engines on it or maybe 4, 2 on each wing. Well, look what we've done. We've taken aircraft now and we're putting multiple propulsors on the wings, which are running at speeds that are right in the structural frequency ranges of these aircraft. So it's also from a safety standpoint. So I talked a little bit about flutter and sort of the structural part of it, but there's also the noise emission and safety. Now, safety is blended throughout this whole process. So let's look at noise emission a little bit. So currently, aircraft, the engines have to go through what's called SECT, Static Engine Certification Test. And as you can see, basically putting a jet engine on a test stand and then putting microphones all around it. Now, HBK's Tessia solution helps to quantify that data, to analyze it in the time and frequency domain. But you also have flyover certification. Here's where we start getting into a little bit of a gray area. By that, I mean the FAA has standards from an acoustic standpoint. Can't be over a certain dB level, setting on the runway, and can't be over a certain dB level when it's flying over your head during landing, during takeoff. Those are clearly defined. Well, from these new electric vertical takeoff and landing aircraft, the actual dB level is very low compared to these jet engines. So the certification currently is not accurate for these types of vehicles. And the FAA is currently working on it to try to come out with new certification rules and regulations, but that hasn't been done yet, especially since these aircraft are not necessarily from a traditional design, meaning they got multiple motors, they got some vertical motors, they got motors that tilt for takeoff and then tilt the other direction to move forward. So you can look at it many different ways. What I wanted to point out here is HBK has got several solutions, from an acoustic standpoint. You can do wind tunnel testing. You can have an array, acoustic array on the ground and fly the aircraft over and do beam forming or use the acoustic camera. Because just because it makes noise doesn't necessarily mean you don't have to figure out where the noise is coming from. So these different tools can help you better understand your aircraft and where the acoustic excitation is coming from. So now let's focus a little bit on the public acceptance. And the reason I said that this could be even a more critical thing is that no matter how safe it is, no matter what it sounds like, if it's not accepted by the public, then a lot of these startup companies are just not going to succeed. I mean, a lot of their business model are air taxis. So it's not only for delivery type things. Now you're going to be getting in them and flying from point A to point B because it's faster, more economical. But if the public doesn't like how it sounds or does not feel that it's safe, then they don't have to use it. So from a sound quality standpoint, I pointed out some things from an exterior standpoint, but now the interior. Obviously, the interior on these, using them for air taxis, it has to be relatively quiet. So you get into sound quality, not only from an interior standpoint, but from an exterior standpoint. And that's why I made the comment here, swarm of bees. So maybe the dB level is not very high, but what does it sound like? And some people may say it's like, oh, well, it could be perfectly quiet. Well, does the public want perfectly quiet? It's really nice for me to be outside and I can hear a helicopter coming from a long distance. So I know it's there. These eVTOL have to be quieter than a helicopter, but I still think they need to have some type of acoustic signature to it so we know they're here, because they are going to be flying very low level, and the quantity of them is going to be a lot greater than what we're used to. The other item I state there, does the sound make you feel safe? So if you look at like the interior cabin noise, how do you want the sound to make you feel when you get in one of these eVTOLs from an air taxi standpoint? If you shut the door and it gives us a rattling sound that doesn't give you confidence that you just climbed into something very, safe, then you're probably not going to want to take the second ride. So HBK has numerous tools to look at airframe, look at transmission loss, look at the noise field for interior, static engine, flight test, exterior, look at quality control, look at your cabin noise. This was a very quick overview from a noise and vibration standpoint, but it doesn't end there. Now, Kurt, I think you have some information and can discuss more from a durability, reliability standpoint, because they are going to be flying fleets of these aircraft.